welcome to everyone for our Cine webinars. And today I'm very pleased to announce Professor Rafael Nagao, my colleague in the Department of Chemistry in the Institute of Chemistry of Unicamp. Professor Nagao, he was born in São Paulo, and he started the university in 2003, the University of São Paulo in São Carlos. And in 2004, he joined the electrochemistry group in the USP under the supervision of Professor Hamilton Varela. He majored in chemistry in 2006, and he also developed a master. He has a master in science. He concluded in 2009. And during the PhD, he spent 14 months in the Department of Chemistry in Massachusetts, USA, under the supervision of Professor Epstein, 2011-2012. He concluded his PhD in 2013, and after that, he was a postdoctoral fellow in the Department of Chemistry in St. Louis University, Missouri, under the supervision of Professor Kiss. After just 2 years of postdoc, he arrived in Campinas in a program of scholarships from FAPESP for young researchers. And after 2016, he is assistant professor in our department. In 2021, he is approved to be an associate professor, and so I'm very pleased to announce my colleague in the same department. So Professor Nagao, he has more than 42 papers in scientific journals with H factor 15, and he has almost 1,000 citations and more than 80 contributions in national and international conferences. So he is also my colleague in the Center for Innovation in New Energies in the division Dense Energy Carriers. And so I am very pleased to present you Professor Nagao. So Professor Nagao, please, could you please give us your talk?
All right, thank you very much, Claudia, for the nice introduction. Let's put my slides over here. Hope it's working well. I think you can hear me well too. So before I start, I'd like to thank also Professor Juarez for the invitation to give this talk, and also the EDCAM team for all the help to prepare for this presentation and everything else. Well, what I'd like to talk today, it's a bit what we have done in the past 2 or 3 years that regards the study of electrocatalysis, mainly the reduction reactions. And the idea is to produce sustainable fuels. So how we can use this strategy to produce sustainable fuels. I'm going to start my talk giving you an introduction and a motivation, trying to convince you that this is a very important topic nowadays. And for this, I'd like to divide in 3 different branches. The first one is how we can define and study the effect of pyridine as an organic catalyst in the CO2 reduction reaction. Here we use a different strategy to elucidate this. The second part is also related to CO2 reduction reaction, but now we try to convert CO2 to formic acid using tin and bismuth nanoparticles. So in this first part of the talk is related more to the CO2 conversion. And then to the third part, we started a new topic that I like very much, that the electrosynthesis of ammonia, which is also a sustainable fuel, the by the combination of two different materials, copper and copper oxides. Okay, and then I will finish my presentation with acknowledgements. Well, the first question that arises is where does our energy come from? So this is an important question, right? So if you look around, you see that in fact most of the energy that we use come from the fossil fuels, right? Fossil fuels, it's the main uh, molecules that we use. We burn oil, we burn gas, we burn coal, right, to generate energy. And to exemplify that, I use some ideas that I adopted from Professor Jaramillo. So it's a very nice presentation. So I put here a little bit different version, but it's very important to exemplify the importance of use fossil fuels. For example, it's extremely abundant. So it provides 5 terawatts of power across the globe. So it's a huge amount of energy. And also it has high density energy density, sorry. So for example, you can drive a car for 6 kilometers, just use one tank of gas. And this is, so if you think of amount of how many liters has your tank for, let's say, for 50 or 60 liters, if you fill everything, you can use and drive for 600 kilometers. This is a lot too. So you can, there's a lot of energy involved here. And also it's equivalent of 8,000 iPhone batteries, just to have an idea of how much energy you put in your car when you go to the gas station. It's a chemical stable, so when you drive your car, you don't worry about exploding, right? So it's safe and easy to store and transport. As a liquid, it can fit any size and shape of the container. And this is a polemic topic here. It's the cost, right? So nowadays, the price of the gasoline in Campinas is around R$ 5 per liter. And but if you look, you compare with another consumer goods, like if you go to supermarket and try to buy, let's say, a piece of cheese or a can of beer, you spend even more than R$ 5, right? So it's not so expensive as you think. So the bottom line is that the, this advantage is the reason why we consume so much petroleum, and that's why it's hard to find a better fuel. It's really difficult to find a different fuel that satisfies everything that I showed you here. And the problem then to burn this kind of fuel is that we release CO2. And if you look over the years, these CO2 emissions increase almost linearly, right? But nowadays we are releasing like 40 gigatons of CO2 per year. This is an incredible, massive amount of CO2. And if you don't have any mitigation policies, this will increase so much that in the end of the century, we will have at least an increase of 5 Celsius degree in the global temperature, having very harmful effects in the climate changes in the earth, right? However, there are some strategies that we can do that here in order to drop down this curve and have a better, let's say, future, a sustainable future for kids. And in fact, we have done this. So in 2015, several countries signed this Paris Agreement, and the idea is to decrease the temperature below 2 Celsius degree and have a net zero emission of CO2 by the middle of 20th century. So if we do that, we think that, let's say, uh, in the end of the century, we can have this temperature, and still we will have an increase of the temperature, but it is not so much. And sorry, if we think that we can find this zero net emission, we find this in the graph around 2070. So from now to 2070, we have like 50 years. So there are a lot of work to do, and I think it's quite possible to do this uh, to break down this acceleration of CO2 emissions. And if you look, Brazil has a 2.48% contribution in total emissions. And this value is actually is not small. It's big amount of CO2. So, but I'm going to show you in the next slides that Brazil has a good potential to decrease this number. And again, as I showed you before, as a greenhouse gas emission, the burn of these fossil fuels always use as an energy source. So the idea is that we have to think, we must think about strategies to develop new materials or new ways to convert into to generate new molecules in a sustainable way that can be used to convert in energy but not result in CO2 emissions. If you think in the United Nations, there are several goals, right, to have a more sustainable world for the future. And in fact, if we look here, we will find the clean energy and the climate action that the points that we are focused on in these later years. And I'm glad to say that we are here in Cine in the dense energy careers. We are very worried about that, and we have been working and with these developments in order to try to have a more efficient catalyst to convert in sustainable fuels and can use and try to help this strategy to get a less amount of CO2 in the environment. And well, one idea, right, to try to consume this excess of CO2 is to reduce that electrochemically. It has some advantages. We can work in ambient temperature and pressure. We can, of course, create these carbon neutral fuels and chemicals, and these can be stored for further usage. So let's say this is our reactor, right? The electrochemical reactor. We can grab this CO2 from the environment that comes from industrial, home, transportation, so on. And during the reaction, we can generate chemical feedstocks, we can generate fuels. These can be stored for long-term usage, and then we can be reused again. But the main problem, so the idea is interesting, but the main problem is to use, we need to use electrical energy because the reaction is not spontaneously. So we need to have some electrical work to do that. And energy, electro energy, it's expensive. However, we can use right now renewable energy, which is less expensive and the price is decreasing along these years. And the most important, I would like to say, is if you compare Brazil with the world, Brazil has some advantages. So we have sun the entire year, we have abundance water, we have wind in the northeast. So we have everything to use these renewable energies and then to try to convert this energy in chemical energy or in sustainable fuels that can be carbon neutral, can turn in a carbon neutral future. But the life again is not easy. We have to think if you want to develop a material, we have to think in selectivity of the material. We have to think about the activity and the stability of this material or a catalyst that accelerate this reaction. And this is not so easy to get it everything together. Usually we get one or two in the maximum. So to get three would be the ideal situation, but it's not so easy to do that. And of course, the reason is if you think in the electrodes, the catalysts in bulk or in a nanoscale, you see that we have to think in grain boundaries, low coordination sites, oxygenated species, roughness, the electrolyte, like the pH, mass transport, the nature of the electrolyte, like the cations, the anions, the composition of the catalyst, the size, the shape. So it's a multidimensional problem. It's quite complicated. And if you think in the reaction, the CO2 reduction reaction, you see that also the standard potentials for the out formation of these organic molecules are very close to the 0 volts, which is our reference where we see the hydrogen formation. It means that you have at least one issue here, that is some kinetic constraints. That is, if you do this reaction, probably you will have a competition for hydrogen evolution reaction. It's a parallel reaction that will consume these electrons for the hydrogen formation. The second point is the thermodynamic constraint. First of all, the CO2 is an inert molecule. It's difficult to break these bonds. And also, the reactions that I show you here is not elementary steps. There are several um, reaction intermediates that participate in the reaction. And usually we have to go for very negative potentials to get the product that you want. So you also have to have large over potentials to trigger the reaction, and then you expend some energy in this case as well. So this is a problem you have to think before design different or any catalyst that you are interested. But if you will look in the 80s, Hori was the pioneer to study this reaction. He made a very systematic study actually, and he showed that, for example, he divided in different groups where the metal has some selectivity. For example, thallium, mercury, indium, tin, cadmium, bismuth, it forms more formate or formic acid. If you use gold, zinc, silver, palladium, you have a more carbon monoxide. If you use nickel, iron, platinum, you have basically hydrogen. But copper has a special property. It basically is able to formate the CC bond. So we have also formation of ethylene or ethanol, propanol, and a considerable amount of methane. And the idea is basically that copper, if you use hydrogen and carbon monoxide as descriptors, you can see that copper can absorb CO without hydrogen. So this CO can dimerize and then have the formation of this CC bond or these C2 or C3 molecules. And some time ago, like 20 years ago, Professor Jaramillo showed that in fact you can observe a very different number of molecules that comes from the reduction of CO2 on copper electrodes. Mainly, we can observe gases. That's the most contribution in this case. But you can observe some liquid products, but in a very small proportion. And this is an example how complicated the mechanism is. It's a simplification, actually, that is a famous paper from Professor Cooper, that we can see that CO2, in fact, can go, if it absorbs by the oxygen, can generate formate. If it absorbs by the carbon forming CO, it can generate methanol or methane, or it can dimerize and then generate ethylene or ethanol. Okay, so it's a very complicated. You have to think in different ways, and the facets, the potential, the pH of the electrode has a very big influence on how mechanism or how which routes the reaction will proceed. Interesting enough is a paper published by Professor Edward Sargent in 2020 that instead of using these materials as a catalyst, he used an organic molecule dissolved in reaction media that can be used as also a catalyst to CO2 reduction. And here it showed that here's like a pyridine molecule bonded by a benzene molecule, right? And what he did was changing the ligands of this molecule and playing with the body charge of the nitrogen, and he see that he got an extraordinary Faraday efficiency of 65% for ethylene formation. And if you will look behind some time ago, you see that Professor Bocaris also did that, but use an even simpler catalyst, that is the pyridine, showing the exact activity to formation of methanol. And the idea is that the pyridine can protonate in the reaction media, forming the pyridine ion, and this pyridine ion is reduced and forming a radical, and this radical can interact with CO2, and then with this interaction, it can go through successive steps of reduction steps, then forming some molecule, organic molecule, like formic acid of methanol. In fact, if we look in the experiments, this experiment that we performed, we see that in blue we have just the CO2 reduction, but then when we add the pyridine, we see a significant increase of the current and a shift of 200 millivolts more or less to more less negative potentials. And this was discussed in the literature. It's a very controversial study. Some of them thinks that the CO2 reduction reaction goes through the pyridine radicals and forming some organic molecule, or there are some people also thinks that the pyridine ion is a weak bronzed acid, and it basically brings a proton close to the surface, forming then the hydrogen, uh, molecular hydrogen as a gas. So what we can see here, we don't know exactly what's happening here, if it's electrons is going to formation of hydrogen, or if this electron is going to formation of some product from CO2 reduction reaction. And the mechanisms are also, there are several proposals, and it's even difficult to understand because some of them are only calculations, but you can see that we can, if, let's say if you have a hydrogen adsorbed on the surface, this molecule can help to formate formic acid, or it can also reduce the aromatic ring, forming dihydropyridine, then can also interact with CO2, forming formic acid or other molecules. And there are some papers that just say that, in fact, the molecule, the pyridine, has a total hydrogenation in the ring, forming piperidine. So the piperidine has been proved experimentally. So the idea was, let's use in a non-conventional way a different technique, so the mass spec technique, coupled in the electrochemical cell. So this is a differential electrochemical mass spectrometry that we built in our lab. And with this, we are able to measure all of these gases. And what we did a cooperation with Professor Fabio Lima from University of São Paulo, where we use we did the experiments here, but we also did these experiments here, where we can also measure these mass specs, but we got a little bit better um, signal noise ratio in this case. Okay, so this is a work done by Igor, Maria, and Adriana, and it's submitted under evaluation. Here it's the conditions we use in the pH 5.6. In this case, we have pyridine in pyridinium ion, some similar concentrations on the solution. We make cyclic voltammetries from zero point 0.1 to minus zero point 0.9 volts versus a reversible hydrogen electrode. What we can see here is the Faraday current increases, right? So when we add especially pyridine, but when we look for the mass charge 2, which is related to formation of the hydrogen, we see that when you have CO2 in pyridine, it increases more when you have just pyridine and just CO2, which is a good indicative that in fact pyridine is bringing these protons and forming hydrogen on the surface. If we measure the mass charge 15, we don't see any signal, so we don't see the formation of methane, so even in the presence of pyridine. But if you measure 26, we'll see that 26 is a mass fragment for formation of ethylene, and the signal is higher when you have CO2 and pyridine. So this would bring us an idea that probably the pyridine is catalyzed ethylene. But if you look at only the signal of pyridine, we have something also here. So this is something you were thinking about and was uh, questioning if the catalyzing pyridine is really catalyzing selectively ethylene. So what we did, so let's look in the mass fragments of the pyridine, and we see that we have the molecular ion 79, we have 52, and in fact we have also 26. And so we have a contribution in mass charge 26. If we plot 52 and 79, we will see that we also have this very intense signal when you have pyridine and CO2, and the profile exactly the same with 52 and 79 with if we compare to mass charge 26. So the idea is when you have CO2, it alters the acid-base equilibrium of pyridine, right? First of all, it competes with the hydrogen, forming carbonic acid. Second, it can be reduced and increase the interfacial pH. So what happens then is that we can shift this equilibrium to the left and we increase the concentration of this volatile species, which is pyridine, and then that's the reason why we see the increase of this signal in both cases. And another thing is we don't see any evidence here, for example, just for in the presence of CO2, we don't see anything increasing observed which would indicate the presence of ethylene. So we don't see, in fact, a catalyzing effect of pyridine, at least in the methane and ethylene. So if it is working as weak acid, let's play with the pH. So we change it for the more alkaline pH to 7.5, 7.5. Again, we have a more formation of pyridine solution. And this is the graph that I showed before, and this is the graph with the pH 7.5. So you can see that it changes completely. Uh, we have a kind of suppression of the Faraday current when we have pyridine. We see that the hydrogen formation with pyridine and without pyridine decreases. So it seems for us that we have a kind of inhibition effect from pyridine, and we don't also see any evidence of methane formation even with the presence of pyridine, and we don't see any evidence of CO2, sorry, any evidence of ethylene formation even in the presence of pyridine, even knowing that here we have a contribution of pyridine. So we also try to analyze the mass charge for the pyridine. So this is 5.6. If you look on 7.5, you see that you don't see anything, and the reason is simple, is that again we have a alkaline pH, it shifts to the formation of more pyridine, which is volatile. The concentration of this species is saturated on the surface. What happens then is that this is basically crossing the membrane and reaching the mass spectrometer. And what we see is that it becomes independent of the potential. And as the concentration is continuous, so the molecule is continuously flowing from this the membrane, we use as a normalization step using the baseline is set to everything to zero. So that's the reason why it's zero. But here what we have is a continuous flowing of pyridine. So let's say again that we use now minus zero point 0.2 as a negative vertex potential. Here again we see the formation of hydrogen, very expressive formation of hydrogen, and this is happening when you have more of CO2 and pyridine. So both are acting like a hydrogen shuttle. They are both weak acids. They bring these protons to the surface and then they can generate hydrogen. We see now the presence of methane and we see now the presence of ethylene. But when we add pyridine, we see the suppression of the signals. And these we could relate it to absorption of these molecules or even hydrogen. and even show that in fact we don't see any effect of catalytic effect in the production of these organic molecules. What we see is the production of the hydrogen um, using pyridine. So as a partial conclusion, so we see the expressive increase of hydrogen in the presence of pyridine. The solution pH plays a major role in the currents and interfere in the acid-base equilibrium of the pyridine. And the Faraday current increase in the presence of pyridine is mostly related to favoring hydrogen evolution reaction rather than enhancing the CO2 reduction reaction. So we show directly here with this work that pyridine is forming hydrogen in fact. So the second part I'd like to discuss is again about CO2 reduction, but now forming formic acid using tin in bismuth nanoparticles. This is work done by Maria, Igor, James, and Gabriel. And so we make synthesis of these materials using a solvable thermal synthesis method. Basically, we use the metallic salts that we want. Then we add some reducing agents like sodium boron hydride, keeping inert atmosphere using nitrogen. And we play with different proportions here. So we use tin bismuth in a mixture of tin bismuth. So this is the Xrd profiles of the materials. We see basically here that you have the metallic phases for tin, the metallic phases for bismuth, of course some small peaks for the bismuth oxides and tin oxides, and for the tin bismuth we didn't observe an alloying effect. In fact, we saw a formation of the metallic phase of both materials, tin and bismuth, some small peaks for the presence of these oxides. We also did the XPS. Just for the tin, we see the presence of oxides in the metallic phase. For bismuth, we see the formation of bismuth oxides. And for the mixture, we also see the oxides in the metallic phase, and for bismuth, also the oxide in the metallic phase. So what we can extract from this is actually the XRD show us that you have mainly the formation of a metallic phase, but in the surface measured by the XPS show us you have a more the presence of the oxide species. We did some microscopy using electron microscopy and mapping, EDX mapping. Just for the tin, we can see a little bit of agglomeration, but overall, all the elements seem to be very dispersed. The same for the bismuth and the tin bismuth nanoparticles. We can see that they are more or less actually well spread over the samples. And we did the cyclic voltammetries. The voltammetries are very similar what we see in the literature, agreeing well with the literature. When you add CO2, it gets us a little bit larger currents. Okay, but when we do for more negative values, what we are interested, we see that the catalysts are very active. So we have the increase of negative values for tin bismuth in tin bismuth. And we did then the electrolysis H-type cell. So this is our setup. And this is our the electrolysis. We correct the ohmic drop, we correct for the pH, put everything in the hydrogen, reversible hydrogen electrode scale. And we can see that as long as we go to more negative values, we increase the currents. This is more expressive for the tin. And so what we did then, we used the HPLC, make a calibration curve for formic acid, took some samples after 1 hour, and analyzed the Faraday efficiency and the activity for these materials. So this is the Faraday efficiency. We can see that bismuth and tin starts to increase around minus 0.5, and tin reaches a plateau around 6 Faraday percent, 60%. The tin, the bismuth increases a lot, so it's a very hard to beat this material. It reaches around 100%, but it starts to decrease when you go for more negative values. The combination of tin bismuth has a lower Faraday efficiency, but becomes interesting when you go to minus zero point 0.9 to 1 volt. So if we look then in terms of activity or the current associated with the formation of this, now the bismuth is not so active for this formation of formic acid. We see that tin is something better in all cases, but now the combination of tin and bismuth is also going better when we go for more negative values. So this is a clear example that in fact you can have good selectivity, but sometimes you can don't have a good activity or vice versa. So to have everything is a very difficult task. But we can see depending of what you want, you can use one type of catalyst in or another. So this is basically what I said here. And the perspectives is we think we should redo again the microscopy images, try to understand a little better, to have a clean images for the morphology of these particles, and TM to have again the size, the shape, and maybe the composition of these particles. Maria is also evaluating the electroactivity in the gas diffusion electrode flow cells, and this is a cell that she built. And the nice thing here is that you don't need to dissolve CO2 in the electrolyte. CO2 goes as a gas phase behind the electrode, and then we can reach much larger currents, like from 10 to 30 milliamperes per centimeter square that she got. And also we would like to analyze the stability of these materials during long duration electrolysis. So the third part, and finally the last part of my talk, and I would like to talk a little bit about the ammonia synthesis. So this is has been done since the process that was proposed by Haber-Bosch, right, where it's possible to synthesize this molecule, basically use nitrogen and hydrogen, and it can formate ammonia, and it's an exothermic reaction with minus 92 kilojoules per mole. So this is the setup. If we look here, we use a very extreme conditions. You have to preheat the gases in high pressures, in let's say 300 atmospheres, and you go through this. The gases go through in this catalyst, aerobase catalyst, in a very large temperature, 500 degrees Celsius. So it's a very extreme conditions. We have to use a lot of energy to keep this, and also, so for example, you have to use nitrogen. Nitrogen is actually easy to get from the air, but from the hydrogen, you have to use methane steam waveform and a gas shift, uh, water gas shift reaction. So, and both reactions generate CO2, and this is a problem, as I said in the beginning. So, because you can contribute for this greenhouse effect, right? So it consumes 2% of global energy output. It's very demanding, and produce 500 million of tons of CO2. Besides, per year we consume 176 million of tons of ammonia, and it's expected to increase to 1.2 billion of tons by 2050. So we really need to think about how we can develop different strategies or different type of technologies that are sustainable. They don't use so much energy and also don't produce CO2, because ammonia is quite important, right? And it's important because of what? The uses, as you know, is based on fertilizers. So it's basically feed the world. used by refrigeration, explosives, and textiles and pharmaceuticals. But what I'd like to show, in the future, this will be used for other things. Will be used, for example, as a fuel in the fuel cells, and also for the direct combustion engines, like for airplanes or even for airplanes for ships. Okay, and if you take a look in the energy density of this molecule, so here in gray it's a carbon-based fuels, in green is a zero carbon fuels. You can see that ammonia has a very large energy density comparable to methanol, and even higher than hydrogen, which is the fuel of the future, right? Because we can bring with one nitrogen, we can have three hydrogen atoms. So it can work also as a hydrogen carrier besides the use as a green fuel. So the idea to synthesize that would be more or less like CO2. We use this renewable energy that Brazil has a good potential, make the water splitting, producing hydrogen, and then again make an electrochemical process that we can use hydrogen and nitrogen forming ammonia or CO2 neutral ammonia. But to break this triple bond from any2 is not easy at all. So it requires 941 kilojoules per mole. And we have to consider other limitations, like the solubility is low, is 0.02 grams per liter. The rate of formation here in electrochemical experiments in an order of 10 of power minus 8 to 10 of power minus 14, so it's very low. And the Faraday efficiency is around 32.24%. So I have to say, actually, I mentioned that July this year, there is a group in Australia that published a Nature paper that say they claim that they got 100% of Faraday efficiency. And so maybe these are kind of overcome, but we still think it's very difficult to surpass these limitations, right? So what we'd like to do is work in a more easier molecule, and we use nitrate. Nitrate is behave like in the same. It belongs to the same cycle of nitrogen, but has lower energy to break this bond, the 204 kilojoule per mole. The solubility 40,000 higher than the nitrogen. The rate is at least 100 times higher than nitrogen, and the Faraday efficiency is even higher. So this is a work done by Gabriel, Maria, and Igor with cooperation of Professor João and Professor Nirala. And what we did here, we did the electric position as the formation of the catalyst. We used a basic media. We put copper sulfate and lactate. When we apply a negative current, the potential oscillates spontaneously. And what we see is a deposition of copper oxides and copper oxides in alternated manner. And we make a cross section of these fumes, and we see that they are mainly formed by nanopores. Okay, and the distribution of copper and oxygen is kind well dispersed on the also in this film, and we can also prove by using the high resolution microscopy that we have the domains of these copper oxides and the copper by the interplanar distance measured over here. And the interesting thing here, when we do the cyclic voltammetry for 1 to 10 cycles, we see that in the presence of nitrate or in the absence of nitrate, the cyclic voltammetries are something unstable, and it decreases along the time. So we were thinking that maybe it could be the reduction of the oxides or some the poisoning effect that decreases the active sites of the surface, then decreases the current. And then we performed some analysis. We made the SEN and AFM mapping. We can see that before the electrolysis, we see this formation of clusters with round shape, with nanopores. And when we do the electrolysis, this becomes more smooth. So the catalyst is changing somehow. And using the AFM, we see the roughness decrease actually, and the potential that's related to working function changes as well, which indicates that it's not just the structure of the surface, but also the electronic structure of the composition of the material is changing superficially. We did the XPS. We see the copper is present along with the copper oxide. But when we do the electrolysis, this copper oxide disappears. We also measure the EDX, and we can see basically the same thing. We have the oxygen before the electrolysis in the red after the electrolysis, so indicating that the oxides are being consumed. And we also perform some Raman in situ. And overall, what we see that if we apply a negative potential in the presence or absence of the nitrate, we can see that. So you see the OCP, the presence of the peaks related to the oxides. Sorry, the presence of the oxides. And then when you go to negative values, we see the disappearance of these peaks, and which indicates again, but now in an in situ condition, that we don't have more of this, at least it's being consumed somehow in this negative potentials. What we did then, we tried to analyze the selectivity of these experiments, making a 1 hour electrolysis. And so if you only analyze copper, you see that it forms mainly nitrite, okay, over the potentials, and the ammonia starts to become more expressive, more negative potentials. If you work with just the oxide, we see that the nitrite is forming a very large Faraday efficiency in lower potential, but decreases as long as it gets more negative. And the ammonia starts to increase, reaching a maximum 0.5, and then decreases. But when you have both, the combination, the situation is completely different. We have a very good suppression of Faraday efficiency for nitrite, and we have a higher formation of ammonia in less negative potentials. So if you measure here, we have 65.9 in minus 0.5. Here we have 66.3 in minus 0.4 with this rate. So although we have this modification of the surface during the application of negative potential, when we have the oxides, we clearly see that it's not converting everything for copper. We have a synergistic combination here, in this case, that can induce a very good Faraday efficiency in less negative potentials. Okay, so this is basically what I said here. And as perspectives that we are doing right now is to certify the origin of produced ammonia, and we are doing NMR. We intend to do FTIR to see what is the electrochemical route for the ammonia. And this is an interesting thing that Gabriel is doing, is regenerate this oxide in an in situ condition in order to evaluate the effect on the Faraday efficiency. And also he plans to work with microfluid fuel cells, with electrolyzer, in order to improve this catalyst performance. All right, so it's basically that. I'd like to thank the support institutions to make it possible this type of research, and especially the financial agencies, in case FAPESP, for the scholarships and projects. And I'd like to thank the collaborators, Professor Fábio de Lima from University of São Paulo, Professor João Batista de Souza from LNano, and Professor Nirala Singh from University of Michigan, to discussions to help in the experiments and everything else. I think without them it was not possible to do this research, and especially for our group. So these are the people who really do the work, and they are daily in the lab working hard, and sometimes in difficult conditions, even with the pandemics. So I'd like to highlight this, that they put a significant effort to make this work really possible. And I would like to invite you to visit my website if you would like to know a little bit more about us. And feel free also to send an email if you want to discuss and to make questions, everything. Okay. So thank you very much, and I think that's it.
Okay, thank you, Rafael, for your inspiring presentation. And as I would like to ask the audience if you have questions. So, I think you can see the question, yes, Rafael?
No, let me see here.
No, you can see the question from Juliani. If you did you measure the conversion percentage of CO2 to hydrogen and to ethylene about the work with pyridine? This is her question.
Did you measure the conversion percentage CO2 to hydrogen and ethylene? We haven't measured uh, using GC. We use just the mass spectrometry, that in this case was more qualitatively measurement. What we can say for sure, that we didn't see any evidence of ethylene formation, just hydrogen formation. And then that's why we attribute the effect of pyridine as a weak acid, not as a catalyst in the CO2 reduction reaction.
Okay. I have a question. Have you tried imidazole? Because Bocardi also worked with imidazole and it's much less toxic than pyridine.
We haven't tried that, but yeah, I think we have seen some papers about that, and I'm not remembering right now if there is a good efficiency for these molecules. And so what I think is interesting, and I saw this in the Sargent works, was that although you have this molecule dissolved on the solution, what is happening really is that this molecule polymerize over the surface,
Mhm.
and then this can act as a catalyst. So I think that the catalyst has to work as a kind of a polymer, not only just as a molecule. And probably if you use imidazole, this could happen too, if there is some activity. But for now, I'm not a member.
Okay, thank you. Okay, so please, um, more questions. So I'm trying to follow here in the chat. Okay, so please, where are my my students of my group? So please, could you please propose questions? And
People are very shy.
yes, I think so. Yes, I think so. People are very shy. So great. Um, let's see if. Okay. Well, so what about your perspectives for the the fuse production from CO2 and from um, nitrogen compounds. What do you think is a better choice, a better efficiency, or more easy to for a large scale production? What do you think is using CO2 or using nitrogen compounds? What do you think is easier to be in the market and so on?
Yeah, my feeling. So for the CO2 perspective, my feeling is that the topic has been studied for a very long time, and the 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 number of materials that has been proposed, it's a very large number. And I think that in this case, I think we have reached a period that we can, so we are mature enough to try to scale up this process. And if you see the literature, the main researchers that work with that, they are trying to make kind of moving for different topics. So I feel that we reach a situation that we can start really do the scaling up and use this a more commercial way, because I think they found very good solutions already. And for this, I think maybe the most promising, which has good Faraday efficiencies, is formate or formic acid and carbon monoxide. I think would be very promising. I think that the molecules, liquid molecules like with CC bond formation, they are much more complex, and we really don't understand very well, I think. And the Faraday efficiency is not so high in order to apply that for a commercial perspective. On the other hand, if we look for the reduction of nitrogen, so I saw that some weeks ago, the most downloaded papers or most cited papers, nitrogen reduction is one of the most cited papers. So people are trying to look for this right now. But as I said, the reaction is extremely complicated. I think CO2 very complicated, but nitrogen reduction reaction is much more. And not just because you work with gases, but also because you need to apply a very large potentials and get like a 2-3% of Faraday efficiency. But so this paper that has been published right now, that they use lithium to catalyze the reaction, and they say that they got 100%. So this opens different perspectives that I think would be interesting to explore in a scientific manner, at least right now. And I would say that for this scenario, it would take more time to develop and upscale this process. And yes, yeah. So hopefully, I think that now with Cine can you or Pablo, I don't know, can bring bigger scales, right, to and make some cooperations to have a more commercial applied system.
Okay. Thank you. Yes, a lot of challenges. So is a lot of subjects to investigate. Yes. So we have a lot of things to have fun
Hmm.
working that field. Okay. Thank you. So I'd like to know if someone would like to ask more questions, comments, and then please. Okay, so we'd like to thank you, Rafael, and thank you very much for your talk today, and thank for everyone for participate of this conference. And okay, great. I think it's We have an excellent talk today. Thank you.
Thank you very much. Thank you, Claudia.